Good day. We're doing lecture number 9 today in CEA 207, and it's all about the shear design of reinforced concrete beams. I'm sure that the majority of you have seen ligatures across beams as I've got in this drawing over there, and I'll just get a page out of the tutorial notes that I'll be showing you later today to show you what a beam looks like in actual fact with the shear steel in it. There we have one. There the ligatures are. There a side elevation of the beam is. Where the shear is higher, we've got these ligatures at closer centers, and we're going to be going through that today and doing the design for that. But that's a ligature. N12s, high tensile 12mm bars in this particular case. What we'll be doing, and I'll be showing you in a worked example and in the tutorial, is how we actually compute the amount of shear steel that we need. So to recap, and I'll read this out to you, reinforced concrete must, in addition to resisting bending stresses, which is, as far as we've got so far, is catered for by the tensile reinforcement in the bottom of the beam, where the positive, wherever there's tension in the cross section of the beam. So these, we must also resist shear, bond, and torsional stresses. Torsion being the twisting of a beam, actual twisting. Now, shear forces are generally resisted by the use of ligatures or stirrups. These are them there. You've probably all seen them in a reinforced concrete structure, where the nominal shear capacity of a section is exceeded. So if we go over the nominal shear capacity, we have to put ligatures in. But actually the code makes us put a basic number of ligatures in anyway. All reinforcement must be fully anchored in the section to enable full design stresses to be generated. And this is achieved by anchoring steel past the point where it is no longer required. The study of this characteristic is called bond. And I would imagine that you've been covering this in Revit, where you've detailed reinforced concrete structures. I will be touching on it again in the future, but it is an important characteristic. Now, shear or shear failure adjacent to a support is shown below. The second sketch demonstrates the principle of stirrups being used to resist shear failure. Additional shear resistance is provided by the dowel action contributed by the horizontal steel. This is a steel that you've been designing to date. Your maximum shear forces are near supports. This is a support there, the reaction, and concrete tends, and they've done many laboratory tests, concrete tends to fail in shear like that. And from that you can see what these ligatures do. They actually sew or weld across this cracked section. They tie the section together like that. In addition to which, we have the dowel action, which is the bottom reinforcing steel is also stopping failure due to shear. Now there's a beam that hasn't cracked, but that's a potential shear crack line. And the shear strength of a beam is stated as 5 VU. VU equals the shear resistance of the concrete plus the shear resistance of the steel. That's what VUC and VUS is. VUC could also be the shear strength of the concrete, as I said, the shear resistance and the shear strength of the reinforcement. DO is the effective depth of the tensile reinforcement. Up to this time we've been calling DO a little d, dimension from the top of the section down to the center of the tensile reinforcement, small d. In doing these shear calculations we'll be calling it DO. A VUC, which is the strength of the concrete, is derived from experimental data and summarized in an empirical formula, i.e. VUC equals beta 1, beta 2, beta 3 VC. where beta 1 equals this equation here. And again, I'm not going to labor the theory. And if we have a large compressive force in addition to the shear force, beta 2 comes into account. We're not going to get as involved as that at this stage of the game. AS 3600 clause 824 directs that the maximum shear force to be designed for occurs at the face of the support, and in some instances DO from the support. So what we're talking about is that you can either design at that point or at the effective depth away from the support, because as you can see the concrete is quite strong at that particular point without steel. Clause 825 sets the following rules. If the shear force is less than 0.55 VUC, no shear steel is required unless the beam is deeper than 750 millimeters. And then you have to use minimum shear steel as clause 828. Now these are various rules which you can read up in your copies of the Code of Practice. I'm going to get into actually doing some problems with you and show you how to actually design shear steel, where we will be covering this. The minimum shear reinforcement in beams is covered by this equation there, and the shear strength of a beam with minimum reinforcement is this equation. We will be using those equations in solving the problems that we come across. And the maximum spacing of shear steel is half the overall depth of the beam, but not exceeding 300 millimeters. So what we're saying there is that once your beam gets deeper than 600 millimeters, you're going to stick to a spacing of 300 millimeters. So if your beam was 800 millimeters deep, you would not exceed 300 millimeters with your ligature spacing. But for certain conditions of shear, the spacing may be increased to 0.75D or 500, whichever is the lesser. I think in our case we'll stick to this rule there at this stage of the game. Now, shear reinforcement must be continued for a dimension D past the point where it is no longer required. So where you no longer need shear reinforcement, you continue it for a dimension which is equivalent to the depth, overall depth of the beam. Now we're getting into the real stuff. Worked example, the reinforced concrete beam is specified as follows. The breadth of the beam is 350. The depth is 600. So what we're looking at is a beam that looks like this. Like this. Breadth of 350 millimeters. An overall depth of 600. An exposure of A1. So working out A1 as we've done previously and working down to the actual, getting to DO, which for shear, as I said to you, is equivalent to the small d you've been using in the past. This is DO there. You will work out your cover for exposure A1, which is 20 millimeters, your ligatures, your distance to the center of the steel. As I said to you previously when I was talking to you, if you have two layers of steel, which in this particular case you have, that's what's been specified like that, your DO will now go to the centroid of those areas of the two layers of steel. There. DO will go to there. And the question that's being posed to you is, calculate the maximum permissible shear force you can put on the beam, the shear capacity with no shear steel. When we say no shear steel, we do include the dowel action from your positive reinforcement. And then the shear capacity with minimum shear steel, that's the ligatures at 300 centers. And then where we have a real shear problem near the supports, we have to work out what the spacing of N12 ligatures are for the maximum shear force. So let's go through this step by step. The first thing we're looking for is the maximum permissible shear force that you can put on the beam. If you exceed that, you'll have to increase the size of the beam. So that's the very first check you do. Now the maximum permissible shear is the shear depth DO, equal to 600 minus 76, 524 millimeters. DO equals 524 millimeters. And VU max, as we said previously in a page back, is 0.2 times the allowable cube strength of the concrete, crushing strength, the breadth of the beam times the effective depth to the centroid of the reinforcing steel. 0.2 is a constant from the code. So you've got 0.2 multiplied by the allowable cube crushing, the actual cube crushing strength of 28 days, 32 MPa. Breadth of the beam is 350 mil. The effective depth in there is 524, multiplied by 10 to the power of minus 3 to bring it into kilonewtons, and we get a figure of 1174 kilonewtons. Now that's far higher than the 330 kilonewtons, which is the shear that's actually been imposed on this beam. So the beam is of adequate size. That's what we're saying. The beam is of adequate size. We now check number 2, the shear capacity with no shear steel, but with the tension steel in the bottom. That's not been written in there, but that's what we're doing. The shear steel ratio PV equals the area of steel divided by the breadth of the beam times the effective depth. And the area of steel of those 6 N28s is 3,720 square millimeters. Divided by the breadth, 350, your effective depth, DO, 524, and it gives you a factor of 0.02. From chart V1, and I'll just dig that chart out. From chart V1, where is it when I want it? I shall find it now. It's at the back of these notes, I think. Yep. If we have a factor for PV of 0.02 from chart V1, so PV is 0.02, V1 in this particular case will be 0.59 for a 32 MPa concrete. So there you have it. 0.02 is somewhere up there, and we get a factor of V1C of 0.59. So 5 VUC then, from the formula that we're given, is small v1c BVDO. We use this factor multiplied by the breadth of the section, multiplied by the effective depth, and we get a figure of 108 kilonewtons. So what we're saying, in fact, is that this beam at the support, where we've got 6 N28s, can safely take a shear force across there of 108 kilonewtons. That's what we've computed. The third thing that we've got to do is we have to work out the shear capacity with minimum shear steel. Now the minimum shear steel is going to be the standard spacing of ligatures without taking into account the closest spacing that we will need to resist the maximum shear force. So according to AS 3600, the ligature spacing must be the least of 300 or half the depth. And I've been over that with you before today. Then the shear capacity with N12 ligs at 300 is given to you by this formula there, which is 108. That 108 was what you worked out previously. That's the shear resistance with only the tensile reinforcement, plus 0.7, which is a standard factor for pi, times 0.6, a factor of 0.6, times the breadth of the section, the effective depth, 10 to the minus 3 to bring it to kilonewtons, and we get 185 kilonewtons. So what we're saying is this beam, with tensile reinforcement it has, with ligatures at 300 centers, which is the minimum amount of ligature, has a strength of 185 kilonewtons, which of course is less than the 330 kilonewtons that we're designing for. So our next step, in step 4, is to actually find out what spacing of ligatures, it says N12 bars, that should be ligatures, of N12 ligatures we need for the maximum shear. So the shear capacity required by N12 legs, 5 VUS equals V, which is the shear force given to us in the question, minus 5 VUC, which we worked at 108. This part there is the strength of the beam with the tensile reinforcement. Don't confuse that with the standard spacings of 300 millimeters. We've discarded that. We have to now close the spaces up on the ligatures. So what we're looking for is we're looking for a spacing that will give us the difference between these two shear forces, which is 222 kilonewtons. We have to design ligatures to resist that force. So 5 VUS over DO equals 222 times 10 cubed over 524, which is DO, gives you a figure of 423. So looking at chart V2 now, here it is. At chart V2, 5 VUS over DO equals 423. 5 VUS over DO equals 423, which is somewhere there. We shoot across to an N12 ligature there. And we come down there, and it's approximately 150 millimeters. It's always safer to err on a closer spacing than on a slightly higher spacing. A spacing of 150 millimeters is a nice spacing for the steel yard to use when they set this up and weld the steel cage together. So that's how you get your ligature spacing. Use those two charts. It's all pretty straightforward. And in an examination, you'd be asked a question similar to this. In our tutorial exercise, we asked to actually do an isolated reinforced concrete beam, specified like this. And you'll find that in your notes that on Connect. The question. The dead load, 80 kilonewtons per meter, live load 105. Show and calculate the bending moment and shear force diagrams, the area of steel, the N12 ligatures required, including adjusted spacings for full beam length. So you've got to work out where you only need standard ligature spacings and where you need extra close spacings to cater for the highest shear stresses. Draw the beam and reinforcement showing stirrups and tension steel. And at the beginning of this lecture, I actually showed you a sketch of what I had done. So that ends the, this drawing here on a two-span beam shows you where you can curtail steel. Curtailing steel means where you can actually reduce it. And this is all according to the code. You don't have to carry all your positive steel through to a support on a two-span beam or even a single-span beam. But at this stage, that's perhaps a bit of academic interest to you. So that's the end of your lecture.